Again, good afternoon, everybody. Hope you are healthy and safe. First of all, I will thanks from organizing committee for inviting me, and a special thanks from Praveen. The title of my presentation is Efficacy of Crystalline-Free Methionine as an amino acid by single meal chickens. This project was a part of my PhD student, which had been done in last year. If it is interesting for you, you can refer to, for complete information, you can refer to published papers in the last volume of British Poultry Science and Iranian Journal of Animal Science. In this slide, you can see outline of my presentation. I'm going to clarify a big products based on this outline and differentiation between crystalline amino acid digestibility and utilization or efficiency of amino acid. Generally speaking, amino acids are essential for normal animal and poultry growth. The amount of some amino acids in feed ingredient are less than poultry requirement. Therefore, they called limiting amino acid and should be added to the diet as a synthetic one. Inclusion of crystalline-free amino acid in lower crude protein diet decrease financial cost, price of diet, and nitrogen excretion as well, which reduce growth and nitrogen retention, possibly caused by significantly lower utilization of synthetic amino acid compared to those bound to protein in feed-restricted animals. Single meal fed meat-type birds, such as broiler breeders and turkey breeders, of course, sometimes broiler and turkey, are subjected to feed restriction in the rearing period and must consume their meal during 20 to 30, maximum 1 hour once a day. Scientific research documents show that during single meal feeding, free amino acids are rapidly absorbed and metabolized before intact protein. Consequently, the efficacy of free amino acid utilization is reduced and the requirement is lowered by about 10 to 30% of its original levels. If you look at to this figure, Nonis and Goss from the University of KwaZulu-Natal in Africa investigate about utilization of synthetic amino acid by broiler breeder hens. As you can see in the horizontal axis, with increasing the level of methionine and lysine, efficacy of utilization of methionine decreased. For each extra gram of dietary free amino acid content per kilogram of diet, the rate of lay and egg output decreased by 3 and 25% per gram per day, respectively. And the efficacy of the methionine lysine as well decreased by 4.3%. Given a debate over the use of crystalline amino acid, a solution is needed. One approach can be balance the arrival of free and protein-bound amino acid at the site of absorption by developing a slow-release amino acid compound, which would establish an equilibrium between the gut, blood, and tissue with regard to utilization for protein synthesis. I mean, we need balance instead of in the diet or in the intestine, we need balance in the site of production, I mean, tissue like breast muscle, brain, and so on. An alternative approach would be use the potential benefit of protein sources with the high concentration of essential amino acid to substitute for crystalline amino acid in practical diet. So, except for the research of nonis and goats, there is a lack of data in vivo, in vitro, or meta-analysis studied investigation the efficacy of free and bound protein for amino acid utilization in single meal fed animals. Thus, as methionine is the first limiting amino acid in poultry, the following study evaluated the potential of feeding protein-bound methionine in comparison with crystalline amino acid, crystalline-free amino acid on performance, absorption kinetics, and efficacy of protein and amino acid utilization in single meal fed meat-type birds, I mean broiler breeders. Okay, you can see, I will explain about our methods and materials we use. A total of 121-day-old female Prospective broiler chicken obtained from a commercial hatchery were used as a model of broiler breeder hens from 0 to 60 days of age. This model was chosen because, I mean, instead of broiler breeder, we use their progeny, the broiler, because the modern commercial strain of broiler breeder have similar genetic potential for fast growth as a broiler offspring. The chicken were fed at libitum with commercial starter and grower mash diet for 38 days. After this period, restricted amount of the diet in pellet form. We use pellet form to reduce the time of feed consumption were provided the last 3 weeks, I mean, until 60 days of age. In order to achieve the same intake and feed consumption time, I mean, cleanup time, to imitate a single meal provision at 10-day adaptation period was applied to all birds to ensure consumption of a constant amount of feed. We distribute 90 gram per chicken once daily at 8 a.m. and they consume the feed during 7 minutes plus minus 2.5 minutes according to the following procedure I will explain for you. In the first 4 days, feed deprivation transitioned from 2 hours to 8 hours per day imposed through feed and light restricted period. For subsequent days, feed and light restriction were gradually increased to 8 hours and 16 hours, hours respectively, so that the end of the adaptation, at the end of adaptation period, the 8 hours light was applied from 8 a.m. to 4 p.m. Feed restriction, of course, does not mean inadequate nutrient, but provide the exact supply of nutrients needed to achieve weight gain according to the management guide recommendation and avoid obesity as well. Then on the 38 days of age, all chicken were weighted and randomly allotted to the treatment diets in the experiment in a completely randomized design with 4 cage replicate containing 5 chicken each, as you can see in the picture. All diets were formulated to isoenergetic and isoproteinous, isoexogenous. Approximate analysis of dietary ingredient and experimental diet was performed according to the procedure of the AOAC. Sorry. The amino acid content was analyzed by ion exchange chromatography. We use special methods for methionine and amino acid sensitive to oxidation. Next slide. Oh, you can see the treatment. Experimental treatment contained 6 dietary treatment, which consists of different proportion of protein-bound methionine to DL methionine, I mean synthetic methionine. The basal diet contains no synthetic methionine. 1.6 gram per kilogram DL methionine and 0.4 protein bound, 1.2 synthetic, 0.8 protein bound, 0.8 synthetic, 1.2 protein bound, and 0.4 synthetic and 1.6 protein bound, and finally, the 6th treatment was 0 synthetic and 2 gram per kilogram protein bound methionine. This amount, as you can see in this table, added by using canola meal and fish meal, as you can see, from 0 in basal diet and increase to 100 gram per kilogram in the last treatment. And you can see the amount of methionine in the basal diet 3.2, 4.6 in the first, 4.4, 4.1, 4, and 3.7 in the last treatment. Another thing, before diet formulation, the different protein sources were analyzed for total and digestible amino acid content to determine sources with high concentration of protein-bound methionine to compensate for any decrease in supplemental DL methionine in the experimental diet. Based on the result, the best protein-bound methionine sources, which include canola meal and fish meal, were selected for the use in the present experiment. The measurement, the parameter we measure, feed intake was constant, as I mentioned before, 90 gram once a day per bird. throughout the 3 weeks of each experimental period. Body weight gain, and feed conversion ratio were measured weekly for each group and reported for the experimental period. At 59 days of age, 2 birds from each replicate were randomly selected and blood samples were taken via the wing vein before feeding. Then only for the first 3 hours after feeding. The methionine concentration of deproteinized plasma samples were determined by reverse phase high performance liquid chromatography. At 60 days of age, again, 2 from the rest of the birds, 2 birds per replicate were randomly selected. Blood samples were taken after 20 hours feed withdrawal. Of course, they access ad libitum to their fresh water. The serum reduced glutathione and oxidized glutathione were determined by colorimetric assay using a commercial kit. For homocysteine measurement, after separation of the plasma from the blood, samples of 2 selected birds per replicate at 60 days of age, the level was determined using reverse phase high performance liquid chromatography. And also at 38 days of age, at the beginning of the experimental period, after raising chicken and allowing them to cage on chicken from each, 1 chicken from each replicate closest to the average body weight of the cage randomly selected as a baseline. It underwent feed withdrawal, but again access to the water, ad libitum water, permitting got clearance, reweighted the next day and slaughtered by CO2 inhalation, and we freeze the whole carcass, whole body, whole chicken, the fresh chicken. The whole carcass were then completely frozen, as I mentioned, at 60 days of age at the end of the experimental period after weekly raising. 1 bird from each replicate was randomly selected, again slaughtered the next day by CO2 inhalation and then frozen. Frozen basal and final carcass were cut, means 3 times, homogenized, dried using a freeze dryer, ground and analyzed for crude protein, ether extract, ash, and also amino acid as well. The carcass amino acid content was measured using reverse phase high performance liquid chromatography. To determine nitrogen content, the excreta from each case was collected during the last 4 days of the experimental period. After slaughter, the ratio of body weight and body component weight were measured. The breast weight was calculated as a ratio of carcass weight, and the liver and abdominal fat weight were calculated as a ratio of carcass weight, including viscera. Let's go on the result. As you can see in this table, due to time limitation, I should go faster. Gross performance of the chicken was significantly affected by dietary treatment. As protein-bound methionine substitution significantly increased body weight, you can see with substitution from 0.4 to 2.4 kg, and weight gain as well, and also the feed conversion ratio was better with substitution of the protein bond. And also you can see the significant difference between dietary treatment and basal diet. Dietary treatment had no significant effect on carcass, breast, liver, and abdominal fat. In this picture, you can see the effect of the treatment hours after feeding. At the start, 1 hour, 2 hours, and 3, and plasma concentration of the methionine. And also you can see the effect of dietary treatment. So in this picture, we can see the effect of time after feeding and dietary treatment. I mean, substitution of the protein bound methionine instead of crystalline amino acid. With regard to the trend of plasma methionine content over 3 hours after feeding, increasing the level of protein-bound methionine substitution in dietary treatment caused plasma content increase steadily. You can see the permanent increased from 0 to 1 and 2 hours after feeding, at 1 and 2 hours after feeding, then decreased significantly at 3 hours. Orthogonal polynomial contrast showed that there was a quadratic response in plasma methionine content in different time after feeding, so that the content of plasma methionine increased up to 1 and 2 hours postprandial, then decrease at 3 hours after feeding. The early peak concentration of plasma methionine at 1 hour after feeding with DL methionine, you can see here. 1 hour after feeding, this graph is for DL methionine 1.6, and then decrease sharply. Compared to the 1 and 2 hour postprandial level at this point, you can see this point and this point, indicated that crystalline free amino acid was absorbed more rapidly than protein-bound methionine. In this table, you can see the effect of dietary substitution with a graded level of protein-bound methionine for DL methionine from 39 to 60 days of age on blood parameters of single meat type chicken. The replacement of the protein bound in the diet significantly affected serum ratio of reduced glutathione to oxidized glutathione, whereby the lowest ratio was found in chicken fed the basal diet. You can see 2.8 compared with those fed protein bound methionine. In addition, protein bound methionine replacement significantly decreased plasma homocysteine. You can see from 36 to 25 micromole per liter. And for serum aspartate aminotransferase and alanine aminotransferase content, none of these compounds were affected by protein-bound methionine substitution in the diet. We can interpret our result. Dietary inclusion of the synthetic methionine from 0.4 to 1.6 gram per kilogram increased the plasma homocysteine concentration from 25 to 36 macromole per liter in the previous slide. as you see. You can see again. The substitution of protein-bound methionine in the diet decreased the plasma homocysteine content. This result could have been due to the positive role of the protein-bound methionine for balancing intestinal absorption of the methionine to improve protein and amino acid utilization. Homocysteine is produced by, as you can see in this picture, homocysteine produced by demethylation of the methionine. But the important point is that, again, homocysteine should be transurfulated by an enzyme, C-beta S, cystathione beta synthetase. But it is important, never mind, excess methionine in the serum can inhibit this enzyme. So the amount of homocysteine increase in the blood and make homocysteinuria. So the result of homocysteine in the blood, our measurement in the blood, confirm our result about the efficacy, better efficacy of the crystalline amino acid, the protein-bound crystalline protein-bound amino acid in compared to crystalline amino acid. In this table, you can see the effect of dietary substitution with the graded level of protein-bound or synthetic amino acid, synthetic methionine, from 30 to 39 to 60 days of age on whole body composition. Protein-bound supplementation had no significance on whole body ether extract, as you can see in this column, and the ash content in the chicken. However, there was a numerical decrease in ether extract content with increase in protein-bound methionine substitution. Body protein content significantly increased with the protein bound methionine substitution, as the highest amount of this parameter was seen for birds fed highest amount of protein bound methionine. Another point is that dietary replacement of protein-bound methionine caused a linear increase in the content of, you can see the probability, the p-value for linear was significant. Dietary protein-bound methionine substitution increased protein utilization and decreased excreta nitrogen as well. This confirmed the positive role of a protein-bound source of methionine for improvement of the amino acid pattern at the site of protein synthesis. I should emphasize at the site of protein synthesis, not in the diet or in the intestine or in the blood. You can see the effect of dietary substitution of protein-bound methionine or synthetic methionine on amino acid utilization. Dietary treatment had significant effect on efficacy of methionine utilization. You can see 69% compared to 44%, and you can compare with basal diet 0.6 or 60%. The efficiency of other amino acid utilization, such as serine, glycine, arginine, alanine, aspartic acid, and lysine, significantly increase with the substitution level of protein bound in the diet as well. The addition of protein-bound methionine resulted in a linear response in the utilization of methionine, serine, threonine, arginine, alanine, lysine, and another you can see in case of methionine, serine, as well as in alanine and lysine as well. I have to say this was because of the difference in absorption rate of the free and the protein bound lysine and imbalance of amino acid at the site of protein synthesis when feeding crystalline amino acid in the diet. It would appear that the synthetic free form of methionine is not utilized in single meal type birds and should not be used in their feed. Regarding other amino acids, the efficacy of utilization was similar, so that measured for methionine. In fact, the decrease in amino acids utilization with dietary DL-methionine and increase with dietary protein-bound methionine substitution clearly observed. This result indicated the positive role of the protein-bound methionine source to improve absorption and creating balanced amino acid supply at the site of protein synthesis. As a take-home message, due to the lack of synchronization in absorption of the synthetic free methionine or other amino acid and protein-bound amino acid in single meal fed animal like broiler breeder, free amino acid is used with low efficiency of utilization. That was a paradox I talk about this at the initiation. Therefore, until the suitable source of the free amino acid is introduced for co-absorption and using as a commercial product in the industry, the protein-bound amino acid can be suggested as a preferred source of supplemental amino acid in the single meal fed mid-type birds. I will thanks from my good teamwork, Dr. Zamani and Dr. Baziani for their collaboration and contribution. And finally, thank you for your attention. Any question, I am at your service. Thank you.